So this is going to be another U substitution problem. How are we going to do a U sub? What are we going to sub out?
Should we factor the difference of squares, the x squared minus 1?
Nah, there's no need to do that.
Okay.
So what we're going to do is we're going to U sub out that thing that's inside the square root, like we did with a couple other ones. And that gives us that du is equal to 2x dx, right? Everybody agree with that?
Yeah.
Okay. So now as I rewrite this integral, I've got an integral of, I'm going to write the x squared, and I'm going to put a 2x there. And so the x and the x squared make that x cubed that I had, right? But I did throw in an extra 2, so I'm going to have to put a 1/2 out there. Everybody good with me doing that?
Yeah.
Okay.
Yeah.
Cool. So now we can take this 2x dx, turn that into my du, and have 1/2 the integral of x squared u to the 1/2 du. But we still have the problem of we've got an x squared in with our u and our du. And so how are we going to go about fixing that problem?
Another U substitution.
We could try to do another u substitution, or we do like a v substitution, but that's not going to work. So we want to think back to that one that we did the other day with we had 1 minus sine squared x, and we turned it into 1 minus sine and 1 plus sine, and we still had like that sine x term in there. What did we do yesterday to deal with that extra sine x term that we still had in there?
Did we solve for x squared on the u equals x squared minus 1 equation? And then plug that in?
Exactly. Yeah, so we're just going to use this and say we know that x squared is equal to u plus 1. And so we're going to just go in and replace that x squared with the u plus 1 to give us 1/2 the integral of u plus 1 times u to the 1/2 du, or 1/2 of the integral of u to the 3/2 plus u to the 1/2 du. Everybody good there?
Yep.
All right, now it should just be a nice simple integral. U to the 3/2 becomes 2/5 u to the 5/2. So we got 1/2 of 2/5 u to the 5/2. And then u to the 1/2 becomes 2/3 u to the 3/2. I should put the plus a constant there. I almost forgot that. And if we distribute the 1/2 through, that becomes 1/5 of u, which was x squared minus 1 to the 5/2, plus 1/3 of x squared minus 1 to the 3/2, plus our constant. Good or no?
Good.
Good.
Excellent. Let's do another one. Yeah, x to the 5th root x squared minus 1. So that's very similar to the last one, except it's x to the 5th instead of x cubed. So our process is going to be almost the same. We're going to let u equal x squared minus 1 and have du equals 2x dx. So this can become 1/2 and then a 2x in there. And if I pull an x out of the x to the 5th, that leaves me with x to the 4th root u dx. And so now what's going to happen?
You can do, we're gonna have to do like multiple substitutions because it's like an x to the 4th instead of x squared.
Right,
Like
x to the 4th instead of x squared, but we still know that x squared is equal to u plus 1. Well, what's x to the fourth? X to the fourth is just x squared squared, right? Or u plus 1 squared. So we can still find a way to do that substitution. Easy enough?
What happened to your 2x?
My 2x dx became my,
Oh, nice. I see.
and so now this will become 1/2 of an integral. Let's see, this is u squared plus 2u plus 1. And if I distribute a u to the 1/2 in there, the u squared will become u to the 5/2. And the 2u will become 2u to the 3/2. And the 1 will become u to the 1/2 du. Everybody good with that?
Yep.
Yeah.
All right, sorry, I was trying to get my kid to turn down his background music. I don't know if you guys can you guys hear that music like constantly in the background?
No, we don't really hear anything.
Not really, no.
Ah, that's good. All right. Well, it's distracting me. So, all right, let's integrate this. We got 1/2, and then u to the 5/2 ought to be 2/7 u to the 7/2, and 2u to the 3/2 ought to be u to the 5/2 times 2/5, so 4/5 u to the 5/2, and then that last one ought to be 2/3 u to the 3/2. Plus our constant, and if we distribute the 1/2 through and do our substitution back to x squared minus 1, we end up with 1/7 x squared minus 1 to the 7/2 plus 2/5 x squared minus 1 to the 5/2 plus 1/3 x squared minus 1 to the 3/2 plus our constant. Any questions on that? Everybody okay with that or no? So if we want to integrate sine cubed theta times cosine theta, this one should just be a u substitution. So the simplest way to go about this is to say, if I let u equal sine theta, then du ought to be cosine theta d theta. And I've already got cosine theta d theta there. So I'll just turn this into the integral of u cubed, right, sine cubed, times my cosine theta d theta, which is du, which ought to just give me u to the 4th over 4 plus a constant, or sine to the 4th theta over 4 plus c.
Thank you. That was so much easier than I thought it would.
Is
Not too bad.
is there a way of knowing?
All right, so this one looks tricky, especially because there's no antiderivative of inverse tangent that we've talked about. But if we think about inverse tangent, we know what its derivative is, right? What's the derivative of inverse tangent? It ought to be 1 over 1 plus x squared dx. And so if I write this out, that's effectively what I've got. I've got inverse tangent x times 1 over 1 plus x squared dx. And so I can just substitute out the inverse tangent x as u, and the 1 over 1 plus x squared dx is du, and get u squared over 2 plus a constant, giving me inverse tangent of x squared over 2 plus c. if we have the integral of natural log of x squared over x, we hopefully recognize that if u equals natural log x, then the numerator would just be u squared, and du is 1 over x dx. So there's your 1 over x dx. It becomes the du, and this just becomes an integral of u squared du, or u cubed over 3 plus a constant, or natural log of x cubed over 3 plus your constant.